Welcome to part 2 of the module on operating system support for programming concurrent and network software. In part 1 of this module, we presented an overview of some of the operating system mechanisms that are available for programming networked applications. We focused on Select and we focused on the Socket API. In this part of the module, we're going to present an overview of the operating system mechanisms available to implement concurrent applications that can process multiple requests simultaneously via multiprocessing and/or multi-threading. As before, there won't be any source code examples in this part of the module. We'll cover many programming examples later on. Let's first start by talking about operating system multiprocessing mechanisms. A process can be viewed as a unit of resource allocation and protection. Resource allocation in the sense that certain resources, typically memory, file descriptors, signal handlers, and so on, are often allocated inside of a process, and protection in the sense that a process is typically fenced off from other processes by memory management unit protection mechanisms built into the hardware. You'll see that there's a number of different kinds of common operations that most operating systems support with respect to multiprocessing. One of the first set of operations we'll look at are process lifetime operations. These are used to create new processes and a new address space in which to run programs. If you take a look, for example, you'll see that in Unix, you have a couple of functions that are commonly used to create processes. These functions are fork and exec. On Windows, you see something a little different, does somewhat the same thing, called create process. In both cases, you typically have a parent process that will create child processes. The parent process can arrange to ensure that the child processes get certain resources when they are started up. For example, it can start them in a particular working directory. It can pass certain command line arguments. It can pass certain environment variables. It might also, in some cases, be able to pass open file and socket descriptors and handles that can be used and inherited by the child in order to do its thing. Likewise, the child process also has a couple of responsibilities with respect to lifetime as well. Children can choose to terminate themselves voluntarily by running off the end of main or calling exit, or they may end up being terminated involuntarily via various operations like signals on Unix or terminate process on Windows. There's also a number of different ways for processes to synchronize their interactions with each other. This use of the word synchronize and synchronization is a little different from what we'll talk about later when we talk about thread synchronization. What we're talking about here is the ability for parents to wait for their children to go away. You might want to wait to find out what your child exit status was so you can know whether it succeeded or failed in order to be able to perhaps respawn it or do something else in some adaptive way. On POSIX and Unix platforms, you typically use system functions like wait and wait PID. On Windows, you can use functions like wait for single object or wait for multiple object. There's also a number of property operations that processes support to do things like change the protection for default file operations, change the user ID of the process in order to be able to gain or reduce various privileges, set the amount of resources that can be allocated, change the scheduling priority, set the current working directory. These are the kinds of things you do most usually if you're doing systems programming. So that's what a process is. Processes are fairly heavyweight to create, and for that reason, modern operating systems also provide things called threads. A thread is basically a unit of computation. If a process is a unit of resource allocation and protection, threads are units of computation that run in the context of a process. And typically, a thread will have resources like a runtime stack, some registers, and perhaps some other things that it keeps track of, its priority, and so on. But threads can also share certain information with other threads by sharing memory, sharing signal handlers, sharing other types of resources like open socket handles and file descriptors and so on. There's a couple of different lifetime operations that you can do with threads. First and foremost, you can create them. When you create a thread, you typically pass in a function to run and also possibly some data, usually a pointer to data, that will be used when the function starts to execute. With modern versions of Unix, you would typically use things like pthread create. With Windows, there's a number of different APIs, create thread, begin thread ex, and so on, which do more or less the same kinds of things. There's also ways to terminate threads. You can have a thread terminate itself voluntarily, either by running off the end of the function that was used to launch it, or by having a thread call an exit function, like pthread exit or exit thread on Windows. You can also, in some platforms, terminate threads involuntarily. For example, you can use pthread cancel on some POSIX platforms. You can also use terminate thread on Windows. You have to be very careful, however, when you start trying to terminate threads involuntarily. And that's because threads may end up holding certain resources, like locks or files. And if they're terminated involuntarily, those resources may end up being corrupted. So you have to be very cautious before you use these involuntary thread termination operations. Some other things you can do with threads is you can synchronize on their completion. So there's a couple of different models here. One model is called a detached thread. In this case, the thread that spawns a detached thread just ignores it, and the detached thread does its thing, and whenever it decides to go away, either voluntarily or involuntarily, any resources it allocated on its runtime stack and registers, any return value it might have, just disappear. Conversely, there's also something called joinable threads. In this case, if you spawn a thread that's joinable, then at some point somebody, perhaps the thread that spawned it, perhaps another thread, will come and wait for or join with the thread when it exits. And that allows it to be able to synchronize on thread exit, as well as be able to get back the return status of the thread to indicate something about whether it succeeded or failed. Different operating systems are quite diverse with respect to whether they support both detached and joinable threads. So you have to take a careful look at your operating system to know which capabilities are supported. This is yet another reason why using patterns and frameworks and reusable wrapper facade components can help make it easier to write portable applications, because those wrapper facades can take care of masking those different diversities and heterogeneity among operating systems from the applications and services that you write. Some other things you can do with threads are use their property operations. These do things like set the thread priority, set the scheduling class. Many operating systems support different classes of threads. You can have real-time threads that run to completion till they decide to relinquish control. There's other scheduling classes called time-sharing threads, where every 50 milliseconds or 20 milliseconds or 10 milliseconds or whatnot, the operating system thread mechanism preempts the thread and switches over to someone else to give it a chance to run. There's also an operation capability on most thread packages called thread-specific storage, which look like global variables to applications, but in fact are allocated out of thread-specific resources that are tucked away inside the implementation of each thread and its thread control block. And you can use this for certain things that need to be global in appearance, but local in their implementation. And we'll talk more about some patterns, like the thread-specific storage pattern later, that can be used to make it easier to access thread-specific storage. So to summarize this section, modern operating systems provide concurrency mechanisms that allow multiple processes and threads to execute. And these mechanisms make it easier for you to write concurrent programs that can take advantage of the underlying cores or CPUs you may have at your disposal. And they also make it easier to be able to write applications that can block for periods of time without starving out other things that the application or service is responsible for doing. It also turns out that using the native mechanisms for threading tends to be somewhat fraught with peril. A lot of accidental complexities here, a lot of portability issues you have to worry about. Even within the same family of operating systems, different versions of Unix, different versions of Linux and so on, there may be diverse ways of doing threading, and so it's hard to write portable code. It also tends to be difficult if you try to write code using these APIs to maintain it, to sustain it, to debug it, because a lot of the interfaces are very low level, and there's all kinds of problems with respect to type systems and life cycles and lifetimes of objects and so on and so forth. So as we'll see later in the course, especially in section 3, we'll talk about patterns and frameworks and how they can be used to encapsulate these low-level operating system mechanisms to provide you with much easier to use, and in some cases actually higher performing ways of being able to do concurrency with multiple processes and multiple threads. Finally, this discussion of threads, as with the earlier discussion of communication mechanisms, is intentionally not meant to be comprehensive. If you really want to dive deep into these concepts of concurrency and networking, I recommend you take a look at some of the other resources that we show here, some of the classic books on Unix systems programming or Windows systems programming, or some of the books that we've written about wrapper facades in ACE to be able to encapsulate the low-level platform APIs with easier to use object-oriented components and objects.